Okay, how do we deal with this inversion charge Q sub I? One way to think about it is to recognize that the device we're looking at is basically a capacitor. On the top plate we have the gate electrode, on the bottom plate we have the channel inversion charge. So when you want to know the charge on a capacitor, you can calculate it by taking the capacitance multiplying by voltage. So we have our gate charge equal to negative of the inversion charge equals the capacitance of the insulator, Cox, another SPICE parameter, multiplied by the capacitor voltage, V gate minus V channel. If we translate that into the variables we have on hand, Cox becomes Cox, V gate becomes VGS, and then there's a blank space for something that we'll have to add in a moment. VGS, leave space there. And then we subtract off the channel voltage as a function of position. Actually, this voltage as a function of position tells us that the inversion charge depends on position. Okay, why do we have to leave a space here? Because in our treatment of the MOS transistor, we assume that the transistor channel just begins to form at VGS equals the threshold voltage. So we're ignoring channel charge lower than that required to reach the threshold condition. Consequently, to establish something on the order of zero channel charge at that point, we have to subtract off the threshold voltage here. So we have, after including the threshold voltage, that the inversion charge is minus Cox, VGS minus VTN minus V of Y. So we can do some calculations. Let's do that calculation. We insert Q sub I, the inversion charge, into the former expression for I, minus W over L mu, integral Q dV. We substitute for Q, Cox, constant with respect to V, so it goes outside the integral, VGS minus VTN minus V of Y, dV. This integral you can do because it's not too complicated. We have constant VGS, constant VTN, at least constant with respect to dV. You can change gate to source voltage, right? But the voltage in the channel depends on position in the channel, so that one is a variable. So we have basically constant, constant, variable, integrated with respect to the variable. So, and multiply the constants by the variable. Integral V is V squared over 2. We get VGS minus VT VDS minus VDS squared over 2 when we insert the VDS term. When we insert the zero term, both go to 0, so those are gone. Out in front, we have the W over L mu Cox parameters. These are critical P-SPICE parameters. W and L you can specify directly, or you can specify the mu Cox product, also known as K prime. If you multiply W over L times mu Cox, you can call that another name, transconductance K. Anyhow, what some people like to do is factor out this factor of 1/2 so that you don't have the 1/2 on the VDS. So what that does is it pulls a 1/2 out in front, and we're left with a 2 times 1/2 giving the 1 parameter in front of the VGS minus VTN VDS term. And this form gives us one nice way to express the current flow in the transistor in the linear mode. Notice, as expressed in terms of all the fundamental variables, nobody has any confusion about what's going on, but a lot of people like to use this transconductance parameter K, and some people define it the way I've shown, and you obtain K over 2 outside the parentheses, but other people define K as including the factor 1/2. So depending who you talk to, pay attention to who defines the factor K 1/2. K is 1/2, K is not 1/2. Different textbooks do it different ways. For example, we have textbooks by Franco and Jaeger and Blaylock. They both define K as W over L mu Cox. But other textbooks, such as the textbook by Gopalin, define K including 1/2. So instead of K over 2 out here, you would see a K. Pay attention to that. This is the linear mode. It applies when we have a channel with VGS greater than VTN. It applies when our drain to source voltage is less than the pinch-off voltage or the over voltage, VGS minus VTN. But what happens if we operate the transistor right at point C, where the channel pinches off, where the channel potential equals VDS, which we can plug into this the inversion charge equation, get Cox VGS minus VTN minus VDS. And we could plug VDS equal to VGS minus VTN into this linear mode equation. Either way, you can calculate it. You end up with a much simpler version of the current voltage characteristic I is K over 2 times VGS minus VT squared. VGS minus VT is the pinch-off voltage or over voltage. So we'll often describe this saturation current as K over 2 VOV, or V, the pinch-off voltage squared. The saturation current expression applies with a channel present, VGS greater than VT, and VDS greater than the pinch-off voltage, greater than the over voltage. So that leaves us with three modes of operation of the transistor: linear, saturation, and what's the third mode? Stop the video to come up with the answer, please. Okay, when you come up with the answer, you find out that the third mode is cutoff. So that's too easy. At cutoff, we have zero current flow. There's some comments in your handout about the definitions of K with the 1/2 in Gopalin or K without the 1/2 in Jaeger and Blaylock and Franco. P-Spice and Spice define a parameter Kp equal to mu Cox equal to K prime in Franco, K prime in Jaeger, and twice K prime in Gopalin. So depending on which textbook you use, you need to either multiply or divide by a factor of 2. There's some references in your handout, and then a summary of both the threshold voltage and the transistor current voltage characteristics, both for NMOS and PMOS transistors. Notice this summary shows, it looks like 4 modes of operation. There's actually only 3. So in cutoff mode, we have no current flow in the channel because VGS less than VT means we have no channel. So no channel to conduct between source and drain. So this applies for any VDS. Cutoff, we approximate with 0 current. When the transistor turns on, it can operate in one of 2 modes, linear or saturation. How do you distinguish between the two? Well, in both cases, we have a gate-to-source voltage greater than the threshold voltage. So that just tells us the transistor turns on. To distinguish linear mode from saturation, we compare drain-to-source voltage with the pinch-off voltage, or compare drain-to-source voltage with the over voltage. Lower drain-to-source voltage equals linear. Greater drain-to-source voltage than the pinch-off voltage means saturation. As a result, we have 2 different current voltage characteristic equations. In linear, K over 2 times twice VGS minus VT, VDS minus VDS squared. In saturation, we have Kn over 2 times the pinch-off voltage squared, Kn over 2 times VOV squared. For PMOS transistors, the situation operates very similarly, but as you know, PMOS transistors would have holes. Forming a channel to attract holes needs a negative gate-to-source voltage. So I find it simpler just to switch the subscripts. VGS negative means VSG positive. So for a PMOS transistor in cutoff, we have V source to gate smaller than minus VTP. So a PMOS transistor would have a negative threshold voltage. Minus VTP would be a positive number. By the way, when I say negative threshold voltage, that's for a enhancement mode PMOS transistor. Would have a negative threshold voltage. Then to distinguish the linear and saturation regions for a PMOS transistor, we would compare source to drain voltage with the pinch-off voltage, source to gate voltage plus VTP. Smaller VSD compared to the over voltage pinch-off voltage gives us linear mode. Greater VSD gives us saturation. The current voltage characteristic equations look the same. We just switch the subscripts on VSD, VSG, and make the sign before VTP positive. Okay, now it looks like there's a fourth mode of operation here. It's not. It's just the option, sometimes, particularly when we're using SPICE, to consider that the current in saturation doesn't necessarily lie flat. It may have a slope. The slope comes from the channel length, the effective channel length shrinking with drain to source voltage. So we have a finite slope to that line. We call that slope lambda, basically. And multiply the saturation current by a factor 1 plus lambda times VDS. So if you need to include channel modulation with this channel modulation parameter lambda, by the way, lambda, L-A-M-B-D-A, equals a p-SPICE parameter that you can use for circuit simulation. So if you need to include that, you can using this multiplication factor. We typically won't include it in hand calculations, but every once in a while it comes in handy. Well, there's a introduction to the current voltage characteristics of the transistors, the MOS transistor.